Okay, this one's actually a pretty quick one. It's not a gigantic extension from what we were already doing. Um, so solving equations that require collecting. So far we've done, what have we done in total? We have tested answers to see if they are the correct solution, so where they might actually just tell you the answer, and instead of solving the equation, you plug it in and check to see, is it the answer yes, or is it not a solution no? Does it make the left side equal the right side? Then we did nice simple one-step equations where we did a single thing to both sides, and that got the variable by itself, so we knew the answer. Then we did two-step equations, so we got rid of the constant term first, and then the multiplying and dividing to get the answer. So what we're going to start to look at now is what really actually probably makes equations get to the point where you really need the equation solving skills to do them. When all the other ones you can probably get away with, oh, okay, I just subtract 12 and divide by 5 or something like that, right? But once you get to ones where the variable appears more than once, you really need to be able to follow through the steps. And we talked a bit before about lining up that equal sign. It would mean creating like twice as many slides, but what I probably should be doing is having, for every single line of work, writing the equal sign right underneath first, and then filling out both sides. That is literally what I do when I am solving equations. So, my daughter's in second year at UVic doing math and physics, and when she gets stuck on something and comes and I'm working on a really tricky equation to help her solve that, I still do that as my practice. I preach it to all my students and I do it myself. Start each step with the equal sign lined up and work out what is now on the left and now on the right. Students often try to start from the left and write across to the right, but that's not how solving equations works. It really is what's on the left, what's on the right. So we've got a 3n plus a 5n there, we notice, and we know that we can collect like terms. So this one's fairly simple. Even though the variable appears twice, it's pretty easy to put those together. Remember, collecting like terms, 3n plus 5n, and remember, even though we're too lazy to write it, in front of that 3 there is a plus sign, right? Plus 3n plus 5n, so they're both going to the right on the number line, is 8n collected together. And now we've made it look just like our one-step equations. We have 8n equals 48. What is with the n that we need to get rid of? A times 8. The opposite of times 8 is divide by 8, so we do that to both sides. And we get the 8's cancel out, and we have just n on the left and 6 on the right. Notice, I would like you to notice something. In the first step here, notice I did not change both sides of the equation, right? I just said, oh, these two can go together. 3n plus 5n is 8n. 3n plus 5n is the same as 8n. 48 is the same as 48. So in the first step, I didn't change anything. I just did a little simplifying. Then in the second step, I changed both sides by dividing by 8. 48 is not equal to 6, right? 8n is not the same as n, but because I did the same thing to both sides, the equation is still true, and I get my answer, 6. Over here, same thing, but we're subtracting 7b minus 4b. Those can be collected together. There's also that plus 8 hanging out there, but let's not worry about that now. I would just notice that these things can join together. So plus 7b minus 4b becomes positive 3b plus 3b. And now we've turned this into our two-step equation. We have the b is being multiplied by 3, and then we're adding 8. We know we need to get rid of that constant term first, and the simplest way to do that is to remember that an added 8 on the left becomes a subtracted 8 on the right, but in the back of your mind, you remember that what you really just did is minus 8 on both sides of the equation to make that happen, right? But you don't need to show that. What is 32 minus 8 on the right is 24. And again, what we were just talking about, right? That equal sign comes first, and you say, what remains on the left? Well, it's still 3b. Nothing's happening. What remains on the right? 32 minus 8 becomes 24. B is now multiplied by 3. So I divide both sides by 3 to get rid of that. 3's cancel, leaving just a plain old b on the left. And 24 divided by 3 is 8 on the right. So really barely an extension from what we're already doing so far. Just you're going to collect a couple variables first, and then you have a regular two-step equation. And let's not forget that we can always check our answers. So let's just do that here. There's the first equation we just solved. 3n plus 5n is 48. We figured out an answer of n equals 6. Let's check it out to see if it's true. So separate the left side and the right side, like so. 3n plus 5n is on the left side of the equal sign. 48 is on the right side of the equal sign. Plug in n equals 6 for all of the n's that appear. And this is another one of those ones where the right side happens to be already worked out. But remember, we will definitely get ones where there's variables on both the left and the right. And now we just got to work out 3 times 6 is 18. 5 times 6 is 30. So 18 plus 30. Add those together. Sure enough, we did get the correct answer. Right? And so this is the beauty because of equations, because if you accidentally got n equals 10 instead of n equals 8, or sorry, n equals 6, and you plugged in 10, you would get what? You get 30 plus 50 is 80, which is not equal to 48. And you stop right there and go back and try and find, because you know you made a mistake somewhere. Yeah, so here's a similar one. Only thing I've done different here is I've separated. So this is a plus 5y and a minus 2y, but we know that we can change the order of those, right? We can do the 5y and the 2y together and the minus 13 at the end. So why don't you guys take a minute and give this one a try. Okay, so I notice I got the 5y and the 2y. Some people might like to move that 13 over first, right? A subtracted 13 on the left becomes an added 13 on the right. If you want to do it that way, there is nothing wrong with that. I'm going to do the collecting first. So here's my equal sign. The added 5y and the subtracted 2y are all on the left side, which means I can collect them. Oh yeah, in front of the 5 we know is a plus. So we have plus 5y minus 2y. So join those together and they become 3y. And the minus 13 is still there. And the 26 hasn't changed. Now I want to make that constant term go away next. So I add 13 to both sides. Or in other words, the subtracted 13 on the left becomes an added 13 on the right. 26 plus 13 is 39. Now divide both sides by 3, and we get y equals 13. Again, if you don't like that with the 13 in the middle, you are more than welcome to take that subtracted 13 on the left to an added 13 on the right away on the first step, and then go from there. There's nothing wrong with that. Okay, now we had a bit of a break on all those ones so far because even though they had more than one variable, the variables were all on the same side of the equation. But we could have variables on both sides of the equation, and we can move these pieces around in exactly the same way we've been moving the constants, where an added one on the left becomes a subtracted on the right, or a subtracted one on the left becomes an added on the right, or vice versa. So here, take a look at this. There's my equal sign. I have some u's on the left and some u's on the right. We cannot combine that 2u, positive 2u, and minus 5u. We can't put those together yet because they're not together on the same side of the equal sign. You can't combine like terms if one's over there on one side of the equal sign and one's over there on the other side of the equal sign. But what we can do is we can take that subtracted 5u on the right and make it an added 5u on the left. Knowing in the back of our brain that what we actually just did was added 5u to both sides, right? We're allowed to do anything we want as long as we do the same thing to both sides. So if I have a subtracted piece, I can add that piece to both sides, which has the effect of making it disappear on one side and appear with the opposite sign on the other side. There. So what we've now done is we've got all the u's onto the same side of the equation. Now we can collect them together. We have plus 2u and plus 5u. Makes positive 7u. And we've now turned it into a regular old two-step equation. We want to make that plus 11 go away, so a added 11 on the left becomes a subtracted 11 on the right. 22 minus 11 is 11. And we still have a 7 multiplied by the u, so we divide both sides by 7. And we don't mind a fraction answer at all. We just leave it as 11 over 7. Or if they say they want a mixed number, 7 goes into 11 once with 4 left over, 1 4/7. If you are looking at this and thinking, I would have moved that positive 11 there over to a negative 11 there right at the start, there is nothing wrong with that. That is actually great. That'll save you a whole step of work. You are more than welcome to do that. In fact, that's what I'm going to suggest in our next slide here, I think. Oh yeah, I just threw this in there randomly. Every once in a while, they might ask you for a decimal answer, right? When they do, then you do punch this into your calculator, 11 divided by 7, 1.571, if they had asked you for 3 decimal places. So all 3 of these are good answers depending on what they want. Never give a decimal answer if they haven't asked for one. If they haven't asked for a decimal answer, they want fractions. All right, so here's the general strategy. You can screenshot this if you want. So I'm sort of taking one step further than what we just did on that example. When you look and you see there's variables on both sides, the quickest way to do it is to get all of the pieces that have variables onto one side by adding and subtracting them across the equal sign, and all the pieces that don't have variables onto the other side. And it doesn't have to be left and right? Like you could put the variable pieces on the right and the not variable pieces on the left if that looks easier. But most students usually like to take the variables to the left and the not variables to the right. Once you've got it grouped, so everything that has a variable is on one side and everything that doesn't have a variable is on the other side, then you collect everything together, and then you just have a one-step equation where you divide to get that final answer. So let's look. Oh, I say to try this one. I haven't demonstrated that yet. You can, if you're watching a video, you can pause and try this. I think, I'm trying to remember if I have one more after this or not. I think I'm going to just carry on and do this because this is the first one like it. So what I look at when I see this is I see there's the equal sign. I got some k's on the left and I got some k's on the right. I got some constants on the left and some constants on the right. So I need to get it so that everything on one side are the pieces with k's and everything on the other side is the pieces without k's. So first thing I've done there, you've noticed, is I reminded myself, just look between those two slides, all I did is I added plus signs. I reminded myself that that 24 is a plus 24 and that 35 is a plus 35, because that helps remind me what I'm going to do is I'm going to take that subtracted 3k on the right and that added 24 on the left, and I'm going to move them across. I want to get all the pieces that have a k on the left in this case and all the pieces that don't have a k on the right. So I look at the right side, 35, that's good. That doesn't have a k, I'm going to leave it alone. 9, that's fine. It doesn't have a k, I'm going to leave it on the right side of the equal sign. But minus 3k, that has a variable in it. I'm going to take that over to the left. Over on the left, 7k is good. It's got a variable. I'm going to leave it there. 24 plus 24 doesn't have a variable. I'm going to make that go over to the right. And so there, I'm going to let you stare at that for a second. You can see the blue subtracted 3k on the right became an added 3k on the left. And the red added 24 on the left became a subtracted 24 on the right. And the effect that has is that all of the pieces that have a variable are on one side, and all of the pieces that don't have a variable are on the other side. And I don't think I have a slide that shows this, but always, 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 even if you don't think about it on every question, you know in the back of your mind, you didn't just magically make this a plus 3k over there. What you actually did is you added 3k to both sides, which made this one disappear and this one appear. And you subtracted 24 from both sides, which made this one disappear and this minus 24 appear. Okay, so everything with a variable is on the left, everything without a variable is on the right. Take out all that color coding because now we're going to do some different color coding. I got 7k plus 3k on the left. I can collect those together. I have 35 plus 9 minus 24 on the right. I can collect those together. And I get, well, I didn't, my equal sign got unlined up there. Sorry about that. It should be lined up. I get 10k equals 20. How do I get the k by itself? I need to now divide both sides by 10 so that the 10s cancel out, and 20 divided by 10 is 2. So there's your strategy when there's variables on both sides. Move the pieces with opposite operations so that all variables are together on one side, all non-variables are together on the other side. Add and subtract them together, and divide to get your answer. And yeah, so I am going to get you to pause and try this. So let's do a check on that. There's the same equation that we just solved. We got an answer of k equals 2. Take a minute, plug in the left side and the right side separately, and verify that k equals 2 is indeed the only number in the universe that will make the left side of this equation equal the right side. Okay, we're going to take the left side of the equation and the right side of the equation. We're going to split them up, and we're going to check them separately. By the way, if you're wondering, why does he do that? Why does Tim do this whole left side, right side? It's because very often when I tell people to check their answer, they just resolve the equation. They follow the exact same steps again, moving the pieces around and isolating the variable. And when they resolve the equation, if they made a mistake the first time, they almost always make the same mistake the second time. So when we check it, we actually don't move the pieces around and solve the equation, so you don't risk making the same mistake. You actually see, does k equal 2? What does k equal 2 make the left side equal? What does k equal 2 make the right side equal? And you can double check that it's actually correct. So we're going to put a 2 in for all those k's. One on the left and one on the right. Over on the left, 7 times 2 is 14, following order of operations. 24 plus 14 is 38. Over on the right, we got order of operations again. So don't go 35 minus 3, don't go 2 plus 9, right? We got to do the multiplication first. 3 times 2 is 6. Now we have all addition and subtraction left, so we have to go left to right. Don't go 6 plus 9 first. 35 minus 6 is 29. 29 plus 9. Boom, 38. So yes, k equals 2. We have double checked. Without resolving the equation, we have actually verified that k equals 2 does indeed make this equation a true statement.